Hello, exercise 12a, looking at convex and concave curves in the main, and also something called points of inflection, which you may or may not have seen before. In fact, this is a point of inflection. So a point of inflection in this case, and this is a very special type of point of inflection. This is called a non-stationary point of inflection. So it implies there's quite a lot to this. We're classifying these in lots of different ways. And as I say, we're also looking at convex and concave curves. So let's have a look. Convex and concave curves. I think probably the best way of thinking about this is what kind of shape it belongs to. So you can see here this curve is on the face of it curving upwards. And I would categorize that as being almost like part of a U shape. You can imagine the U shape carrying on, and I've described this as a minimum point almost. It's not a minimum point because we don't know whether it does do that, but you can imagine it being part of one. And if it's part of one, and this one's likewise one, you've got the left hand half here, but you can see it effectively could be considered as if it's going to go that way. Even if it doesn't matter. It's that kind of shape. We call this a convex curve. The curve might end up doing lots of different things. It might end up doing things like this, But the point being, in the section, now you might almost think of it from there, probably to there. We don't know really what's going on elsewhere, but you can imagine it almost between those 2 points. The curve is convex, but the other part, and again up to about maybe there, I don't really know, a bit higher maybe, because it could be that this curve does something else, I don't know. But between these 2 points, we might consider it concave, because I'm saying a concave curve is one which you might consider to be part of like an end shape or a maximum point. And again, this one here, you can imagine that then curving down, or this one curving down. And I think that's the best way to think of this. This one is definitely a maximum, so it's concave. And you can see this is actually a maximum point up there somewhere. But either side of it, we might consider this to be, in between these 2 points, we might consider it to be concave. The words themselves obviously remind you of lenses and what you see in physics and science from GCSE. But convex and concave, then, I don't think either's obviously which way round it is. I think you just have to remember that convex is like a minimum and concave is a maximum. The good thing about that, of course, is the maximum has an A in it, and so is concave, but that's the best I can come up with, okay, in terms of making sure you remember. Now, one other thing about convex and concave, if we are describing them as being minimum points, there's something we know about a minimum point. And when you find the coordinates of minimum points, you invariably find that dy by dx equals 0, and then you use this fact and you look at d2y by dx squared. And you should remember that d2y by dx squared has to be greater than 0 for convex, or what we're calling convex, for minimum points. And for concave, then, we do a similar trick. Normally we find dy by dx. We set it equal to 0, and then we go, all right, now, using that knowledge of where the x-coordinate is, we find d2y by dx squared at that point. It has to be less than 0 if it's a maximum point. So now we're saying if it's concave, it's also got to have this feature, that d2y by dx squared is less than 0. So let's bear all that in mind. This question says, find the values of x corresponding to the convex section. Now, I've already said to you, concave has got an A in it, so that's like the maximum points. So by definition, the convex hasn't got an A in it, so that must be a minimum point I'm looking for. And minimum points, we know that d2y by dx squared is greater than 0. I always think these are the wrong way around. Minimum you'd think would be low, but it turns out to be the big numbers I want, the positive numbers. So anyway, so it implies that I've got to differentiate anyway. Let's differentiate. I'll get 4x cubed minus 12x plus 3. So minus 12x. And what we do to find this, the obvious thing to do, I suppose, is to differentiate again. d2y by dx squared is 12x squared minus 12. So this will tell me where the points of inflection are, which I'll come to in a bit, but also the d2y by the x squared is. So to find where it's bigger or lower than 0, I suppose my first job is to set it equal to 0 and solve that. It might be better actually if I write greater than 0. I'm half tempted to. I'm going to leave it like that. 12x squared equals 12. Therefore x squared equals 1. Therefore x is plus or minus 1. Now this tells me that I don't know what the curve looks like. I'm sure I'll probably draw it in a bit, but between 1 and minus 1 something's happening. When is it greater than 0, I suppose, is what we should be saying. When is that greater than 0? When is it greater than 0? When is it greater than 0? Now, you've got to be a little bit careful. If you draw an x squared graph, and say when's it greater than 1, sorry. Well, you can see it's when x is bigger than 1, and also when x is less than 1. So I'm going to change my answer slightly here. When x is bigger than 1, or when x is less than minus 1. I should have got the minus there. So it's going to be bigger on those sides. So alright then, so that's interesting. There's two different places where this has got convex sections. So let's just see if that's the answer I wanted. Yes, it is. X is less than 1 or x is greater than 1. Now, I did tell you I had no real idea what this looked like. And this minus 1 and this 1 is here and here. Now you'll notice that we wanted convex, which is minimum points on the graph. And if you type this into your graphical calculator, which you've now got, you can see there are these minimum parts of the graph. This is all minimum, it says. So this section here is definitely convex, and that's everywhere from there. Then it goes into this, what I describe as a maximum section. And notice at the halfway point of these, so it's going up, it's going up, it's coming down, it's still maximum, and then at the halfway point it starts curving back again. Okay, so this is an interesting point in its own right, and then this again on this side is convex as well. And in between it is concave. So this leads us to talk about points of inflection. I've already named them a couple of times. So here, this point here, and this point here, these are points of inflection. These are points at which it becomes, from being convex, it changes to being concave in the middle. So that point is called a point of inflection, and essentially it's a point of change from one type of curve to the other. So this is a minimum point, effectively, and that's a maximum point. So the maximum point side is concave, it's got an A in it, concave. This is convex, and you can see in between we have this point of inflection. Likewise over here we've got what looks effectively to be like a maximum point, so this is concave, this is the other way around, isn't it? And it half turns and it goes, nah, forget it, and it curves back up again. This is the convex part, and this point in between and this point in between is a point of inflection. Now these are different. This is called a horizontal point of inflection. And the reason for that is because if you was to find dy by dx at this point, it'd be equal to 0. Whereas this point, on a non-horizontal point of inflection, I can tell you that dy by dx is not equal to 0, because otherwise it would go straight across. Notice for both of them, d2y by the x squared is equal to 0. d2y by the x squared is equal to 0, because that's our definition. That's what this says up here. So if you go from a convex to concave, or concave to convex, and in the middle you have this d2y by dx squared equal to 0, then that is a point of inflection. So another example briefly, y equals 3 cos x minus x. There's 2 points of inflection between 0 and 2 pi. Find their coordinates. Okay, fair enough, we'll have a look. First job, dy by dx. 3 cos x. Again, you may remember sine cos minus sine minus cos. If I'm differentiating, cos goes to minus sine. So this goes minus 3 sine x. minus 1. Now, it does say to me what points of inflection, so I'm going to leave it there actually. I may well come back to that and set that equal to 0, but for now I'm going to straight away do d2y by dx squared. Now if I do d2y by dx squared, again I've got minus sign, so if I differentiate it, it stays at minus cos, so it's minus 3 cos x. And minus 1 disappears, and we have to set this equal to 0. So therefore cos x effectively is equal to 0. When is cos x equal to 0? We can type that into your calculator, or you can just know from the shape of the graph. I'll type it in, just so I can do the same as what most of you would do. I'm going to do the... I need to be in radians, make sure you're in radians. Angry unit, radians. Okay, so inverse cos of 0, and it comes up as a half pi. So that's my first solution, half pi. You should remember you can find a second solution with cos, usually 360 minus, and here it's going to be 2 pi minus a half pi, which equals 3 over 2 pi. So I've got one solution, I've got two solutions. Now, the only problem I don't really know, well, I don't know my y coordinates for either, first of all, and I don't know whether there are horizontal or non-horizontal point of inflection. And I suppose the easiest way to suss this is just to substitute these two values in. So when x equals a half pi, I can say that dy by dx is minus 3 sine half pi minus 1. And what's that equal to? So I can type in sine of a half pi times minus 3, take away 1. I get minus 4. So that's therefore got to be a non-horizontal point of inflection, because otherwise it equals 0. It doesn't. What about the other one? Are they both going to be like that? When x equals 3 over 2 pi, dy by dx is minus 3 of sine 3 over 2 pi minus 1. When I've done that, I've got 2, as you can see. So that is also a non-horizontal point of inflection, and this is my graph, actually, what it looks like. Now, one thing I didn't find is y. Now, they'd be quite easy to chuck in, put your half pi into the original equation, and you'd get values for them. So half pi and 3 over 2 pi, presumably that's what you get. And notice what the interesting thing, I think these are my turning points. I'm not interested in those. I've actually found my points are there and there, I think. These are my points of inflection. So there you are. So this last example, I don't think we'll finish it, but we'll have a look and maybe finish it in class. The curve y equals x cubed 6 minus x is 2 points of inflection. So just bear this in mind. I don't like it the way it's been written, so I'm just probably going to multiply that out. 6x cubed minus x to the 4. It says it's got 2 points of inflection. Find their coordinates. So we should now know. We differentiate, which is 18x squared minus 4x cubed. We differentiate again. d2y by dx squared is 36x minus 12x squared. We set this equal to 0. We want points of inflection, and it has to be equal to 0. So if I do that, I get 36x equals 12x squared. Divided by 12, I get x equals 3x equals x squared. And probably better actually if I'd left it all on one side. X squared minus 3x equals 0. Therefore x is x minus 3, and I get 2 points with x equal to 0 and x equals 3. Now, as I say, I don't think we're going to finish this. But our job obviously is, now I know where the 2 points of inflection are, we have to determine whether they're stationary or non-stationary, a bit like I did last time. So perhaps finish this off for me, and we'll tidy this up in class. And you should obviously now know what you're meant to do. You've got these 2 points, substitute it in here and see if you get 0 or not. If you do, it's stationary. If you don't, it's non-stationary. And it says hence sketch a curve, which might be a bit of a jump as well. So that's what it looks like, that's what my answers are, and we'll finish this off properly in class.